Okay, they want us to find the torque about the origin right here. We know torque is given as R cross F, where R is the position vector for the point of application of the force. It's being applied right there. The position vector for the point of application of the force relative to the origin about which I'm calculating the total torque is this vector right here. And I can write it down in terms of components by inspection. Let's see, to get from here to there, I got to go 0 distance along the x-axis. So I got 0 times I hat plus I got to go up along the y-axis a distance 0.560 meters. So I got 0.560 meters times j, and then plus I got to come out here along the positive z direction a distance of 0.250 meters. So 0.250 meters times k hat. Copy that down without the 0 there. So I got 0.560 meters times j plus 0.250 meters times k, simplest representation of r in ijk or coordinate unit vector notation. Alright, then all I got to do is then substitute r cross f into this expression. And I got torque tau is equal to this r, 0.560 meters j, plus 0.250 meters k, hat, of course, crossed into the f vector given as this. Alright, it's just a matter of doing that cross product. I've got a couple of different ways of doing it. I'm going to do the cross product both ways. First, we'll use the determinant method. This one is a toss-up on which way is easier. If I've just got one non-zero vector over here in terms of one non-zero term over here, I would probably use the second method that I'm going to show you. With all three of them, I definitely use this first method that I'm going to show you. But when it's 2 and 2, it's a bit of a mix. I think it's about the same amount of work both ways. You should be able to do it either way, the cross product. So J, K. First thing you do, you got to write down this row. This is an actual equation. So this is this determinant is a real mathematical expression. It's not just a scratch pad. It's a different way of writing what we've got up on this line, the cross product. So here I write down first vector first, which is the r vector, just the components on this next line, 0.560 meters and 0.250 meters, of course, with the units, and then it's actually I've got those two in the wrong spot. It's 0I, easier to look up at this line, 0I, and then this J and this K component. So let's go ahead and slide those over. Let me try selecting. I'll do a cut and paste. There we go. And then 0 was here. And up here, it is the I and the J. So 4.00 newtons and minus 1.5. 0 newtons, and then the K is 0 in this case. Alright, now I got to do that cross product. So I've got I times positive down and to the right, which will just be 0 in this case. This times that is going to be 0 by inspection. And then minus down and to the left. But down and to the left we got nothing. I got to continue over here, as if there was another IJK written out there. So coming down and to the left, I'll go ahead and, this was the first piece that I got. And then down and to the left, this one continues over here. And I got a 0.250 meters times minus 1.50 newtons. That's the I term. Now let's work on the J term. So plus J down and to the right. I'll do that one in green here. Down and to the right would be J times the 0.25. And then if I continue down, as if this was copied over down there, I enter into this 4.00 newtons, so I'll have the 0.250 meters times 4.00 newtons, and then minus J stuff down and to the left, but that's just 0 in this case, so we run into a 0 on the way down and to the left. And another 0 over here. This is the minus, and this one was the plus. Okay, so it's just a 0, and then plus, the last term is the K. Coming down into the right, I'll go, this is the plus piece, continues over here as if there was another K written there, so we're coming down here. So that's just a 0. And then minus, the minus piece coming down here, it looks like that's a non-zero term. We got 0.560 meters times 4.00 newtons. So that's our expression for tau, obtained using the determinant method. Just simplify it and multiply those numbers out. We get minus minus, so we got plus 0.375 times I, and then for the J term, that's just 1/4 of 4, which is 1 with a plus sign, 1.00 newtons times J. And then the last term looks like it is going to be negative. We got minus, and that's a 2.24 Newton meters times K. These are all Newton meters, so meters times newtons, meters times newtons. So let's squeeze them in there. We need meters multiplying all these. I just got the newtons. So Newton meters times I, and Newton meters times J. And we already had the Newton meters up there. So this is our answer for the vector tau. I do need it to be a vector on the left. Obtained using the determinant method. And the other way to evaluate this expression, which I'll just copy down, right here. Is multiply it out in what I think of as the normal way. This cross product operator acts like normal multiplication as far as distribution and association properties are concerned, but it doesn't commute. So if you take this crossed into that, you get the negative of what you would get if you did it in the opposite order. They're not the same, so it's the commutative property is not obeyed by the cross product, but the other ones are. So let's take advantage of that. I look at it as just ordinary multiplication. You could use the FOIL order if you wanted to. I'm going to take this first term right here and multiply it by each of the second terms, and then take the second term, multiply it by each of the of these two terms in the second product hand, should say, and see what we get. So we got point. I can change the order of numbers, but I just can't reverse the order of the j and the I. So I got this thing crossed into that. I'm going to change the order around a little bit, interchange the scalars. I can do that with the vectors in order, but you got to keep the vectors in the same order that they start out in. So you can look at it as this times this crossed into this times this, which gives the same thing as this times j crossed into I. And that's what I want to write down, the j crossed into I right there. And then plus, I have this one times this one, which will be 0.560 meters times a negative 1.50 newtons, and times j cross j. You don't actually have to write out this entire line. That is to say, you could replace this all with 0, because any vector crossed into itself is 0. So I'm showing a little extra work here just to elucidate what you need to know. You don't need to copy this line down in its entirety. Instead of j cross I, you could put down what j cross I is, and we'll talk about that in just a second. I'm going to do that on the next line. Plus, yeah, that's all I'll do on the next line, so you know what you got to write. So now we're into this one times that, and then finally it'll be that times that. So I got the 0.25, I'll go plus 0.250 meters k crossed into, except I want to do the k part last, just multiply the numbers first. 0.250 meters times the 4 newtons, and then we're talking k crossed into I. And the last term will be this one into that one, so we got the 0.250 meters times the minus 1.50 newtons, and then it's k crossed into j. Alright, first thing, any vector crossed into itself is 0, so that's just 0. Then I'm going to draw a little circle thing here that helps me remember the algebraic sign for the other ones. You cross any one of these unit vectors into another one, and you get the third one with a sign that depends on what the order is. So the way the order works is if I go around clockwise in this circle that I've drawn with just I, J, and K, looks more like a triangle, but then I get a plus the other one, and if I go the opposite direction, I get a minus the other one. So I'll show you what I mean here. On this first line, I'll just copy that down. We got tau is equal to 0.560 meters times the 4 newtons. J crossed into I. Ji, I'm going backwards around the circle in the negative direction, so I get minus k. J crossed into I gives me minus k. And then I had that plus 0, so I'm all the way down to this one. I'll just copy that part down. Times 4.00 newtons. And then I got k crossed into I right here. K crossed into I. K crossed into I just gives me j, because I'm going clockwise around the circle, so that's a plus j. And then copy that last piece down, 0.250 meters times a minus 1.50 newtons. K crossed into J. I'm going backwards again, so that gives me a minus I. Alright, that's my expression for the vector tau. I'll go ahead and simplify it a little bit. I get tau is equal to, I'm going to have a minus sign there. I get 2.24 Newton meters times the K. So it's that minus sign that I got out front. And then plus this one is entirely positive. That's 1.00 newtons times J. And then this one, I get two minus signs, so that's positive. So that last term turns out to be 0.375 Newton meters times I. And then again, I forgot the meters on one of these. So put the times meters in there and squeeze in a J, and I got it made. And then on the next line, I'll just put these in order. The vector tau, when it's written in unit vector notation, it should be in the order ijk. So I'll take this one first, 0.375 Newton meters, and then plus this one, the J term, 1.00 Newton meters times J. And then finally I got the K term, which is 2.24 Newton meters times the K hat. And that's my answer for tau. Let's see how that compares with the last time we found what tau was. 0.375 plus minus is the first thing I'll look at. And I got plus minus, and then 0.375 and 1, 0.375 and 1, and then minus a 2.24 all Newton meters. So we get the same answers we got the other way, as we have to if we did it correctly both times. Alright, that's a wrap for SAC 318 problem number 3.